Okay, well, let's continue. So we just went over how bones grow in length. Let's talk about what regulates that. And basically, what regulates the growth and length are hormones. So if you look at this picture, I don't know if they're still alive, but this picture, when it was taken, this was the tallest man in the world. And he was actually almost 9 feet tall. So that's the height of, ceilings. That's how tall he is. And then, I don't know, I guess she's still alive, but she was the shortest or smallest person in the world, adult. And when you looked at her, she was like 28 inches tall, which is 2 feet 4 inches. So look, she doesn't even come up to his knees. So there's some huge difference between what's going on in his body and what's going on in her body. And so let's look at this. So what controls growth are hormones. And depending on how old you are, it can be different hormones. But for infants, all the way up to, I don't know, you're about 10 or 11 years old, the hormone is called growth hormone. So growth hormone, or HGH, causes growth, and it causes growth all over your body. So it causes bones to grow, but it also causes muscles to grow. It causes skin to grow. It causes growth in lots and lots of different tissues. Well, right now we're not worried about these other tissues. We're just talking about bones. And so what it does here is it stimulates this epiphyseal plate. So we just went over the epiphyseal plate, and remember, it's got these zones in it. We have a resting zone, we have a proliferating zone, and then there's a hypertrophic zone, calcification zone, and then finally an ossification zone. And so what growth hormone does is it stimulates growth. So it stimulates the cartilage to grow, and it stimulates ossification to happen. So when you look at what it does, that's exactly it. It speeds up cartilage growth rate. So cartilage speeds up, it divides faster. And so it speeds up cartilage growth. It also speeds up ossification rate, but not quite as much. So look, who's growing faster, cartilage or ossification? Which one's happening faster? Cartilage is growing faster. And remember, we're going to build cartilage before we build bone. So the faster we build cartilage, that means the faster the structure can grow. And so because we're increasing cartilage more than we're increasing ossification, bones are going to get longer. But it doesn't speed up either one of these very much. It's just a little bit. And so what we get with growth hormone is we get constant slow growth. Constant slow growth. So if we look at it and we measure how much you grow every year, it's pretty much a flat line. Now, most people think that children go through growth spurts, but they don't. Now, infants do. Infants grow like crazy. So we grow like crazy. But when you reach about age 2 or 2.5, growth flattens out. Look at it. It's almost a flat line. And the average person grows about 6 to 7 centimeters per year. And look, it's a flat growth. Very, very flat. It's slow, constant growth. And that's exactly what this human growth hormone promotes. Slow, constant growth. And so you grow about the same every year. And so if you look at it and you've grown this is about 3 inches a year. And so you can calculate how tall a person is going to be. And look, males and females grow at basically the same exact rate. And that's what happens all the way till you hit this age. But this age right here, something else happens. Puberty happens. So puberty changes things a lot. We're going to go from this flat growth to a different kind of growth. Because what happens at puberty is we get these other hormones that come along. These are the sex hormones. And primarily the sex hormone in males is testosterone. Primarily the sex hormone in females is estrogen. And what both of these are going to do is they're going to speed up growth. So they're going to go to this epiphyseal plate, which was already growing at a slow, constant rate. But what's going to happen is they're going to speed up this cartilage growth, and they're going to speed up this ossification rate. And so all of a sudden now, we're not going to get this slow, constant growth. We're going to get a huge jump in growth. We're going to get a growth spurt. And so when we look at what happens, these sex hormones speed up ossification and they speed up cartilage growth, but it's not exactly the same amount. They do increase cartilage. So you get this huge jump in cartilage growth. But they also increase ossification, and they increase ossification even more. So cartilage is growing, but so is ossification, and it's growing more. It's growing faster than the cartilage growth. So now, who's growing faster, cartilage or ossification? Ossification is. And so, look, ossification is the one chasing the cartilage. And if it's growing faster, what's going to happen is it's going to catch the cartilage faster than it would if this didn't happen. And as soon as it catches the cartilage, remember what happens? It all turns to bone and growth stops. So when we look at this, two things are going to happen. We're going to get a growth spurt. And if we graph it, it looks like this. Here's this growth spurt. But another thing's going to happen. The cartilage is going to be caught by the bone. And so growth is going to stop. So these sex hormones do two things. They promote this huge growth spurt, but they also close the epiphyseal plates. And when you close the epiphyseal plates, growth stops. So two things are going to happen here at puberty. A growth spurt. Oh, look, instead of growing this 7 centimeters a year, it's like this or like this. I don't know what that is, maybe 12. Look at this other one and we can see it. It's like this. We get this huge growth spurt. But we're also going to close the epiphyseal plates. And when that happens, bone is going to stop growing. And so this person is going to have reached their adult height. Well, in general anyway, females enter puberty at a younger age. And so they're going to stop growing at a younger age. And if they stop growing at a younger age, they're going to be shorter. Males, on the other hand, enter puberty at a later age. And so they're going to stop growing at a later age. And so in general, males tend to be taller. But if you look at this, this shows the growth of the whole person. So look at how fast the fetus grows. So the fetus grows like this. So in 9 months, you go from basically 0 to 7 or 8 pounds. That's a huge amount of growth. In fact, it's about 30% of the person's adult height happens while they're a fetus. And then we're going to get infant growth. And infant growth is also very fast. So from 7 or 8 pounds to 20 pounds or something. That's another 15% of your adult height. And then remember, we're going to get this slow, steady growth during childhood. That's about another 40% of your adult height. And then finally, we're going to get the growth spurt. Even though the growth spurt is dramatic and very obvious, it's really not the biggest part of your growth. It's only about 15%. And then finally, growth is going to taper off. Well, look, it didn't hit 0 here. For females, it hits 0 right along here. And for males, it hits 0 out here at about age 25. So females tend to stop growing around age 18. Males tend to stop growing about age 25. Not only do these hormones cause a growth spurt, but they also make the skeleton change. If you look at young children and you look at their skeleton, you look at their stature and you look at them, they don't look very different from each other. Males and females look very much the same. In fact, they don't have any of the characteristics that we think of when we think of males or females. It's not until puberty comes along that we develop those changes. And those changes are a lot of changes. Some of those happen in the skeleton. So we get changes in the pelvis, we get changes in the skull, we get changes basically in all bones. And we develop what we think of as a masculine form and a feminine form, or a masculine skeleton and a feminine skeleton. So if you look at the pelvis, that's one of the most obvious places where there are differences. So if you look at the male pelvis is taller and narrower. So it's taller this way, but it's narrower this way. And if you look inside it here, the opening is much smaller than if you look in the female. The female is shorter, but it's a lot wider pelvis. And if you look inside here, it's a much bigger opening. Another very obvious thing is right here in the front. Males have a V shape right here, whereas females have sort of a U shape right here. Well, all of these changes are because of childbirth, because only one sex gives birth to children. And so if you think about all that what happens in a childbirth, the fetus, the baby, has to go through here to get out. And so you need this bigger opening. You need this wider stance and so on in order for this fetus to make its way out. Males don't have to do that. And so males have a stronger pelvis because of the way the shape is than females do, because they don't have to worry about childbirth. And then if you look at the skulls, look how different male and female skulls look. So the jaw is very different. The chin is very different. There are much bigger, thicker ridges on the male than there is on the female. Even the shape of the skull cavity, the cranium, is different on a male. Teeth are bigger in a male than they are in a female. All kinds of things are different. So when you look at the skeleton, every single bone between males and females is slightly different. And then don't forget, not only does this testosterone and estrogen promote growth, and not only does it change the shape of the bones, but it also closes the epiphyseal plates. And if you close the epiphyseal plates, no more growth can happen. And so we're going to stop growth in height. And so we go back and look at our epiphyseal plate. Remember, that's what it looks like while in a growing bone, but there it is. So this is going to happen because the bone has caught up with the cartilage. They've caught up with each other, and there's no cartilage left. And if there's no cartilage left, there's no growth left. So if you look at an X-ray of an adult versus a child, you can see the difference here, because this is cartilage, and cartilage does not block X-rays. And so it's going to look dark. But if you look at it in a bone, in an adult, there's no cartilage. That's bone, and bone does block X-rays, and so it's going to look white. So if we go back and look at this, you can see these epiphyseal plates right here. Those are epiphyseal plates. These are epiphyseal plates, and you can see them on all of these bones. Whereas if you come over here to the adult, what we see are the epiphyseal lines. There's no cartilage there, none at all. And so remember, I said that you can kind of estimate how much growth a person has left by measuring how thick these epiphyseal plates are. So if a person's epiphyseal plate is this versus this, well, you can say that this person has more growth left, or this one has got less growth left. And so one of the things that sometimes is done is X-ray and measure these epiphyseal plates of children if you need to estimate what their amount of time left for growth is, because children grow at different rates. And remember, part of this has to do with growth hormone. So what if you have very little growth hormone? What are you going to be, taller or shorter? You're going to be shorter. What if you have a whole lot of extra growth hormone? What are you going to be? You're going to be taller. So remember, we looked at those two people. We had this tall guy and this really short little woman. Well, think about what's going on here. He's got a heck of a lot of growth hormone. A lot. And so the bones grew very fast during childhood. But hers, she had very little growth hormone. And so there was very little stimulus for growth. And so she may remain very short. And so that's the main thing that changed these two people's height. So look at this and see if you can figure out which one of these is an adult and which one of these is a child. So A is the adult and B is the child. Does it make sense to everyone? So that's how bones grow long ways. But remember, not only do bones change shape, they get wider. So if you look at a little kid's bone, it might look like that. When you look at an adult bone, yes, it's longer, but it's also bigger. It's wider. And so we're going to have to be able to grow this way as well as growing this way. Well, remember, length happens at the epiphyseal plates. That's not how growth in diameter happens. It happens on here. So this is called appositional growth. So appositional growth is just like we had in cartilage. It's when you lay down new bone on top of existing bone. So we're going to lay down new bone on top of what's already there. Well, there's no cartilage over here, so it can't grow the same way as it did here. There's no cartilage on here. What we do have, though, is the periosteum. And so the periosteum is what's going to cause this growth. Well, when you look at what causes this growth in diameter, the first person to think about this and to look at it was a guy named Wolff. And Wolff actually came up with what now is called Wolff's Law. And what Wolff's Law says, it says that a bone will grow, get bigger in diameter in response to the forces that are placed on it. In other words, if we provide force against the bone, stress against the bone will grow. There's an easy way to remember this, and that is if you stress a bone, it will grow. And when I say stress, I don't mean like yelling at it or something like that. I'm talking about mechanical stress. I'm talking about running, jumping, lifting weights, gravity, things like that. If we place those demands on bones, the bones will grow in response to it. Well, Wolff lived a long time ago, and he really had no way of measuring things very much, but he noticed some things. He did it completely and totally by observations. And what he found out was, when he looked at it, is if you're right-handed or left-handed, that the bones on the side that you use the most are thicker and stronger. So if you're right-handed, the bones in your right arm are thicker and stronger. Another thing he noticed was that when you look at long bones, they tend to be curved and they're thicker right where they're most likely to break. If you pull on bones with muscles and you pull on them very strongly, where the muscles attach, you get bigger projections. You get bigger bony things there to attach those muscles to. And then finally, in spongy bone, you can see trabeculae. Remember, you can see them with your naked eye. They're not random. They form along the lines of stress. So these observations is how he came up with Wolff's Law. So look, if you look at this, we can even see it now. Now we have the advantage of doing something like a bone density study. And so if you look at this, this is exactly what this is. It shows the bone density. And here is the scale here. So the more dense it is, it turns this color. The less dense it is, it turns this color. So look, what this is two people or a person's bones, left and right. And so by looking at this, you should be able to tell, is this person right-handed or is this person left-handed? Which one do you think they are? Johannan says right. Does everybody agree with her? Priscilla says left. Well, remember, look, this over here is the most dense. So the more red you have, the denser the bone is. The denser the bone is, it's caused that because you use it more. So yes, it's the right one. Look at it. There's a lot more of this red right here and a lot less of the purple. This one has a lot more of the purple and blue. So this person uses their right arm a whole lot more. And you can actually measure that also by looking at what happens to the bones of someone who plays racquetball. So what these are densities depending on how much racquetball you play. And depends on when you start is how dense the bones are. So look, if you start playing racquetball after puberty, you gain this much in density. But if you start younger than that, before puberty, you gain this much in density. And then these people don't play racquetball at all. But look how much denser this is than the control. And again, even this is more dense than the control. Well, remember the reason that they grow, according to Wolff, has to do with stress. And so when you exercise, when you jump up and down, when you do things like that, you're putting stress on your bones. And so some exercises are better at building bones than others are. And again, it has to do with how much stress that you put on it. And so if you think about different types of exercises that people do, some are much better at producing bone. Those are called highly osteogenic. Some are not osteogenic at all. And so if you go down the list here, what do all these things have in common? They have things like jumping, lifting weights, and things like that, because your body has weight to it. Jumping, running, anything to do where your feet are slamming into the ground. Those are very osteogenic. But look at this. What do these have in common? What they have in common is you don't have to support your own weight. Something else is supporting you. It's either water or the bicycle. It's something else is supporting you, and so it's not nearly as much of an effect of gravity. So if you want to build bones, these are the kind of exercises you should do. Now these are also good as well, but when you get over here, it's less and less. Now that doesn't mean these exercises aren't valuable. They are. Think about swimming and cycling. They require a lot of blood moving around, and so these are great for your heart. So they're good for things like cardiac health, but because they're being supported and there's no effect of gravity or stress like that, they're not so good for bones. Make sense to everyone? Any questions? So look what happens to bone mass if there is no kind of exercise. So look what happens. So after just 2 weeks with no weight-bearing exercise, look, you lose 5% of your bone mass. 2 weeks. After 4 weeks, look, you lose this much. After 8 weeks, look how much you have lost. So if you just decide, hey, I just really don't want to exercise anymore, I'm just going to sit on the couch and eat pizza and watch TV, it does not take very long for you to lose lots of bone mass. And when you lose bone mass, it's going to make bones easier to break and so on. We also lose mass just because of age. So if you look at age, obviously older people, when you look at these graphs, have less bone mass. And so if you think about age here, right here somewhere is when there's the peak of bone mass. That's about age 30. And it sort of hovers for a while, but around age 40, it starts dropping, and it drops throughout the rest of your life. Well, look, females never have as much bone mass as males do. And females, when they lose bone mass, because they start with a lesser amount, they're going to have a lot less bone mass than the same age of a male. And when you have less bone mass, it's going to make you more prone to things like diseases like osteoporosis. And so we're going to talk about osteoporosis in a little bit. But it's because of this. You can prevent this from happening, though, at least to some degree, by exercise. Because remember, if you exercise, bones grow. And these are the exercises that are the best ones for that. So if you're a female in this class, you should consider doing these exercises before you get to a certain age, because you're going to lose bone mass automatically. But if you start at a higher level, you're going to end up at a higher level. Any questions? And then look what happens when you lose bone mass. There's a certain point where when you reach a loss of bone mass, that your chance of fractures go way up. And you might wonder why old people are a lot more prone to fractures. It's because of this loss of bone mass. But look, you can stave it off. If you're sedentary, you don't ever do anything, this is when you reach this fracture threshold. The average person who does a little bit, this is where they reach the fracture threshold. But if you're an active person, look, it's over here somewhere. Maybe 100. Well, once you fracture a bone and you're old, it's very difficult to recover from that. And so this fracture threshold is a really, really important thing to think about. And then here's some just different body parts that show changes due to resistance training. Look at this. Remember what happens is after a few weeks you lose bone mass. Look, you can see it on an x-ray. So here we are, we're going to start. This is what it looks like. Look at these bones. They're very, very dense, strong. But then with no exercise, just after a couple of weeks, look what happens to them. They start looking like this. And after 8 weeks, they look like this. And it's so much easier to fracture this bone than it would be to fracture that bone. Any questions? So remember Wolff's law. And Wolff's law, remember, said that right-handed people, left-handed people, whichever side you use the most, have thicker bones. That if you use a lot of muscle movement, you lift weights and so on, your bones get thicker where the muscles attach. And remember, it also said that trabeculae form along the lines of stress. And so let's look at these forces, these stressors. So the main forces, the main stressors we're talking about are things that are due to gravity and then due to movement. When you hear the word mechanical, it means movement. And gravitational forces have to do with things like body weight and so on. And so if you look at a bone and you analyze where the forces are, we can see them. Well, there are two kinds of forces on bones. There's the kind that squish the bone, that's called compression, and there's the kind that stretch the bone, that's called tension. So if we look at the middle part of the bone, remember the middle part of the bone is this shaft part right here. looks like this. We're only talking about the diaphysis of the bone. Well, remember the diaphysis has a big hollow space in the middle. Has that medullary canal in the middle. Well, why? Here's why. Because when you look at the stressors, they're all on the outside. Here's where the stressors are located. Here's where the stressors are located. In the middle, there's no stress. And what happens when you have no stress is the bone goes away. The bone disappears. Because you don't need any bone there because there's no stress applied. The stress is only on the outside of the bone. And so that's where we're going to build bone. Because remember, if you stress a bone, it will grow. If you stop stressing a bone, it will go away. So the diaphysis, the only place where we have stress is on the edges. Over here, there's stress. Over here, there's stress. But in the middle, there's no stress at all. And if you have no stress, you don't need any bone. Does that make sense to everyone? Does everybody now understand why there's a medullary canal? It's really just because there's no stress there. So what do you think would happen if I artificially applied stress in the middle here? What if I somehow applied stress in here over time? What do you think would happen? What would happen to your bones? Now there's stress in here. What do you think is going to happen? What's going to happen is bone is going to grow in here. So the bone would look like this because stress would grow in there. And if I did it all the way through, it would look like this. Because when you stress a bone, it grows. Make sense? So in the diaphysis, the stress is only coming from two directions. It's coming this way, that's compression stress. And it's coming this way, that's the tension stress. And so bone is only going to form along those lines. And because the stress is very concentrated in a small area, the bone is going to be concentrated. And so we're going to get dense bone. But look up here. If we look up here, we have a different kind of stress. When we look up here, here's what the stress looks like. It's spread out. It's not like this down here where it's this, and we're only going to get this kind of bone. Up in the epiphysis, this is what the stressors look like. So look, they're coming from lots and lots of different directions, and there's no place where there's just a ton of stress. It's coming from lots of directions. And so we need to build bone from lots of directions, and there's no place where we need to build a ton of bone. So look what we do. We build spongy bone. And look, these stress lines match up with these trabeculae. Look at this part right here where there's a lot of stress. You can see it right there. There's where a lot of stress is. But if you look here where there's very little stress, look, you see very little stress. Does this make sense to everyone? This is a really important thing to know or think about if you're going to stay in healthcare. So when you look at the epiphysis, the stress is coming from lots of directions. Lots of directions. And wherever there's stress, that's where the bone grows. And again, if I look here, look at that versus that right there. And if I look here, look at that versus that right there. You can't see a better observation that shows exactly what Wolff's law says. Any questions? So that's why we have these trabeculae. And that's why we don't have compact bone here and here. And then that's why we have this medullary canal here. That's why, because there's no stress. But on the outside, we have concentrated stress. And then up here, the stress is spread out. And that's exactly the way the bone is. Any questions? So look, if I were to take and overlay this on top of this, you can see exactly stress, bone, stress, bone, and so on. Well, if you look at trabeculae, remember they grow along the lines of stress, but they don't grow in perfect straight lines. And the reason why is the same reason why most of us would not want to sit on this stool. Look at this stool. I wouldn't want to sit on it, would you? What do you think would happen if you sat on the stool and you just leaned forward or leaned backwards just a little bit? What would happen to this? It would collapse. Well, unless I want to build a stool that's solid, like a log, you might sit on it while you're camping, which is really, really heavy, by the way, and hard to move around. And if you had to carry it all day, you wouldn't want to do that. I need some other way to strengthen the stool without making it solid. Well, fortunately, I can increase the strength of this stool 16 times just by adding some braces. So look at this. I added just a few braces here. And what it does, because they stabilize the other trabeculae, I can now hold 16 pounds or 16 times as strong as I could over here. So when you look at trabeculae, we think that they should grow in very, very straight lines. But look, they cross each other. And those crosses, where they cross each other, help to stabilize and strengthen the bone. Make sense? Any questions? So, if you look at this, here's the epiphysis. And look, these are the compression and tension lines. Up here, they're coming from lots of directions. And there's no place where it's concentrated. And so I should build my bone exactly like this. And that's what these trabeculae are all about. But down here, look, in the diaphysis, the lines of stress are only in two directions, and they're concentrated. And so I should build my bone down here just like that. And so I build dense bone down here. Any questions? And then here's what trabeculae look like. We went over this before. Remember, there's no central canal here. So trabeculae don't have any osteons. And then remember what we have are lots of spaces in here. And because there's space in here, we can use it for stuff. And so that's where we keep marrow. There you can see trabeculae. Any questions? Okay, so that's how bones grow, or why they grow. Another thing about bone growth is, remember, it happens throughout your life. And not only do bones get bigger, they get smaller. And not only do they get bigger and smaller, they change shape. They change shape. It depends on what's happening. They change shape depending on the stressors that are placed on it. And so what we're going to wind up doing is, to change shape, we're going to remodel. It's just like remodeling your kitchen or your bathroom or something. In order to remodel, you have to take the old stuff out before you build new stuff. And so we're going to need cells to take the old stuff out before the cells build new stuff. And so remember, we have these two different types of bone cells. We have osteoclasts, and remember, those remove bone. And then we have osteoblasts, and they build bone. So they're going to have to work together. So here's a unit of remodeling. Look, I'm adding bone here. Here's my osteoblast. They're adding bone. So this is going to get bigger right here. But over here, look what I'm doing. I'm taking away bone. And that's the osteoclasts. And they eat away the bone. And so look, if I add bone here and I take away bone here, I'm going to completely change the shape of the bone. And so I'm going to add bone where I need it. Where I need it, where the forces are. And then I'm going to take away bone where I don't need it anymore. It's no longer required. And by doing that, I change the shape of the bone. This part gets bigger and this part gets smaller. Well, again, what's going to control that? What controls it are these stressors. Mechanical stress, remember, that means movement. Gravitational stress, that means gravity, lifting weight, holding your body weight up. Well, how is it that stress can cause growth or cause shrinking? It has to do with electricity. So stress, force, when you apply force to a bone, there's chemicals in here. There's calcium and there's phosphorus and there's things like that. And when you apply the force to that, it creates tiny little electrical fields. Electricity happens. And those tiny little electrical fields stimulate osteoblasts. So in this area, osteoblasts are going to grow. It also inhibits osteoclasts. So even if there are any osteoclasts here, they're going to quit working. So this area is going to grow. But look, there are no forces over here. So if I come down here, there's no force. And what happens with those no forces, no gravity, no mechanical, what's going to happen is I'm going to stop stimulating the osteoblasts. So even though they're still there, they're not going to do anything. They're not stimulated. And the lack of force is going to make the osteoclasts become more active. And so they're going to begin to eat away the bone. So here I get growth. But down here where there's no force, it's going to shrink. So places with force grow. Places with no force, no stress, shrink. And because of that, I change the shape of the bone tremendously. Any questions? Okay, well, I want to take another short break because this is heavy and you need a little bit of time to relax. So let's take another short break and we'll come back again in about 10 more minutes.